guys, and welcome back to Elevate Chem. I'm Jesse, and this is another concept video. This episode is our second in a 5-part series all about equilibrium. And to explore this concept, we're going to be looking at a question because ultimately the best way to learn a concept is by learning how it's applied in your exam. Now, the first thing that we're going to do, as always, is I want you guys to tackle this question first. And this is from the WACE, that's the Western Australian Exams, and it's the Stage 3 Chemistry exam from 2013, guys. And it's question 20. So I want you to download that exam now, have a crack at this question first, and then I'll see you in a moment. So pause the video and have a shot. Fantastic, excellent. So this question was a bit of a worded question here, which is one of the first that we've tackled. In fact, there's actually no calculations that need to be done, or at least really involving numbers. And instead, this is a great example of the fact that you need to understand these concepts and not just be able to plug in numbers. Now, quickly scanning through this question, there's always a little bit of worded text at the start, and I pretty much always skip it because it's not something I need to understand. This here is clearly something I'm going to get around, and it's our chemical equation which is going to be dictating the rest of our response. So let's have a quick read of the question. Indicate in the table below whether there would be an increase, decrease, or no change in the concentration of NH3 gas after the changes given in the table are imposed on the system and equilibrium has been re-established. Provide a brief explanation for the observation. Now, this is actually a pretty critical point here, guys, that it's after equilibrium has been re-established. Occasionally, they will throw in a bit of a weird question when they ask what happens immediately after these changes, but they're saying right here it's after equilibrium has been established. Now, we've already had one video on equilibrium, and hopefully you guys have watched that. And we know that it's all about the dynamic change in essentially the weighting or whether the products or the reactants of this equation is favored. And so we're going to be looking at how some of these changes will affect that point of equilibrium. And the first thing I want to note here is looking at this equation, there's actually potentially one little bit that you guys might not have seen before. And it's this little bit on the right-hand side. And that's saying plus 920 kilojoules, and notice it's on the products there. And what this means is when the reaction is proceeding, it actually releases 920 kilojoules worth of energy. And hopefully if you hear that, the first thing that comes to mind is awesome. That means this is actually a delta H value, which is, of course, negative. And the reason why is it's producing energy, and if my delta H is negative, if my energy being produced is on the right-hand side, it's an exothermic reaction. And I actually really encourage you guys, if you're given the delta H value in the sort of standard format of delta H equals negative 920 kilojoules on the side, I encourage you to actually write it in the matter that they've done here, because it makes it really clear on what side the energy is doing and what that is actually going to cause for a response. So considering the fact that we've got that little energy value right there, I'm actually going to jump into part 2 of this question because I'm going to be talking about that immediately. And it says right here, the temperature of the reaction system is doubled. So one of the important things here, guys, is we're talking about temperature, and temperature also has a lot to do with heat. It's all about energy. So I don't really care about what the components are here. I don't care about the fact that I've got ammonia, oxygen, nitrogen oxide, and of course, water or steam as it's a gas. What I really care about, again, is this energy value that's sitting right over here. And it's saying the temperature of the reaction system is doubled. And what that means is there's going to be an increase in heat energy, and that means it's going to favor the reaction in a certain way. And why I like adding in the energy on that right-hand side there is it means it plays really similar to how a lot of the questions you see might have been structured. So they don't have an exact example here, but for example, one of the classic ones might be to say that, okay, we've removed or added some oxygen from this system, and we know that it's going to favor the reaction to avoid that change. We're using Le Chatelier's principle here, guys. So if the temperature of the reaction system is doubled, that means that there's going to be more energy input into the system. And because there's energy on the right-hand side, because there's energy in the products, that means that it's going to favor the left-hand side of the equation. I just write that as shorthand as LHS. And I'm favoring the left-hand side. Okay, awesome. Now let's just double check that what the question is asking. whether there would be an increase, decrease, or no change in the concentration of NH3. Excellent. So my NH3, that's on the left-hand side of the equation. So if I'm favoring the left-hand side, that means there's going to be an increase in my concentration of NH3. Fantastic. So the reason why I think this is the right way to sort of go about it, guys, is by adding in that heat energy. In this case, the equation has done it for us. It makes it really clear that when I add this heat energy in by increasing the temperature, it's going to favor the left-hand side of the reaction. Excellent. Let's jump into part one now. The volume of the reaction vessel is doubled. And this has sort of potentially two things that could come into it, and we're going to be tackling them one at a time. So the first thing with these questions is whenever we're dealing with a pressure, whenever we're dealing with a volume, which are pretty much the same sort of thing, we're going to be looking at the number of moles of gas and only gas on the left-hand side and also on the right-hand side. The reason why we don't really care about the liquid or about solid, or of course aqueous, if any of those components we're seeing around, is they don't really affect the pressure. You never really hear of a solid being, 2 kilopascals or anything like that. We've got only gases impacting both volume and pressure, or at least to any significance. So let's have a look here, and we see that on the left-hand side, the total number of moles of gas is equal to 9, and I've simply gotten this by adding that 4 and that 5, because they're both gaseous. And on the right-hand side, I've got the 4 plus the 6, so that's 10, and again, they're both gaseous, and I've checked that. So we can see that there's more moles of gas on the right-hand side than there is on the left-hand side. So let's have a think about this. If the volume of the reaction vessel is doubled, suddenly my pressure, and I'm just going to write that as P, is going to drop. And Le Chatelier's principle says that it's going to favor the side of the reaction that will minimize that change. So if my pressure is dropping, Le Chatelier's principle says that I want my pressure to increase as much as possible, however I can. And if we have a look here, pressure is dependent upon the number of moles of gas in a system. And my right-hand side has more moles of gas. So that means to counteract this drop in pressure, I'm going to favor the right-hand side. And if I'm favoring the right-hand side, guys, that means the reaction's going in this direction. What's happening to my NH3? More of that is being used up. So we're going to get a decrease in concentration. Now, some of you might have been sitting there thinking, hey, concentration is also related to pressure. What's happening there? Well, additionally, we've still got the pressure actually decreasing here. And if my pressure goes down, that means, in general, that my concentrations are going to go down as well. So it's still a decrease. Fantastic. Let's jump into this third one here. N2 gas is injected into the reaction system while keeping the volume constant. Now, let's have a look at this equation just for a second here. And hopefully you can see that there's actually no N2 kicking about. And in fact, even if it's not, as it is in this case, a noble gas, a really unreactive substance, if it's not featured within this chemical reaction, you should probably just take a punt that it's a noble gas. Though of course, you can check your periodic table in your data booklet just to confirm. Now, what happens when we inject a noble gas into this system, you might have just memorized that there's actually no change. And I'm going to start off just by writing that. So overall, guys, there's going to be no change. But why is that? So again, if we have a look at the reaction, you notice that if I add N2, it's not going to favor either side of the reaction as it isn't actually featured in the equation. However, the pressure is going to increase. If I'm adding any sort of gas into this system, the pressure has to go up. And you might go, hey, wait a second here, Jesse. Just before you said when the pressure decreases, concentration decreases. So if my pressure increases, then shouldn't my concentration increase? Well, you're spot on, except there's this little interesting extra bit of wording where my concentration is actually related to something called the partial pressure. And the partial pressure isn't the overall pressure of the system, but instead actually the pressure of each of these individual components as a fraction of the whole. And when you add this inert gas into the system, the partial pressures remain constant. And that's the key here, guys. So although it favors neither the left-hand side or the right-hand side, and P increases, partial pressure doesn't change. So that's what's really going on behind the scenes here, guys. You guys might have just remembered, hey, adding an inert gas, no change, that's fine. But again, these videos are all about increasing your understanding. So I want you to understand that, yes, my inert gas isn't actually affecting this chemical reaction, but it is increasing the pressure. However, that doesn't impact my concentration. Fantastic. Let's look at this last example here. Water vapor is injected into the reaction whilst keeping the volume constant. That last bit's pretty important there. But let's have a look at this first little bit of the change. Water vapor is injected. Let's scroll back up to our equation. We notice that water vapor, or steam, is sitting on the right-hand side of my reaction. So of course, when I add it, Le Chatelier's principle is going to try and decrease that addition of water vapor. And that means it's going to be favoring the left-hand side. So that initial add of water vapor is going to favor the left-hand side of the equation. And that is, of course, going to increase our concentration of NH3. But what about this keeping the volume constant business? Well, that means again that our pressure is going to increase. And again, I was talking about the fact that this can impact the concentration if the partial pressure changes. And in this case, because it's not an inert gas, the partial pressure also increases. And that means overall, we're going to have an increase in the concentration of NH3. So what was this question all about here, guys? Well, primarily it was about one of my honestly favorite things in chemistry, which is Le Chatelier's principle. And it's key here that we recognize that it was a difference in concentration versus a change in amount. And you might see that in some questions. And the only thing that changes is you might have to consider the total amount of either volume or moles within a system. And of course, we're looking at forward and back reactions here. And the key thing to really take away is what Le Chatelier's principle means. And really what it means, guys, is a system that is subject to change will do its very best to oppose that change. And the only way it can do that is by either favoring the back or forward reactions. Fantastic. Hope you guys got something out of this. And I look forward to seeing you in the next episode. See you later.